So I'm sitting here with Dr. Patrick Brown. We're going to be going over his paper, Climate Warming Increases Extreme Daily Wildfire Growth Risk in California. Good
This
to
is
have
our
you.
paper, Holt.
Our paper. I am co-author on it. It is called co-author, right? If there's like
Yes.
nice. Yeah.
Yeah.
Very excited to have my name on something official like that. But yeah, I'd say the large majority of the work was put together by you. But how would you summarize this paper if you're just kind of explaining it to someone who doesn't have a background in this field? Just if you had to give them like the quick gist, what would it be?
So we used artificial intelligence, so machine learning, specifically neural networks and random forest models, to essentially quantify the relationship between climate change and wildfire behavior at this high resolution. So at this daily time resolution and at the spatial resolution of individual fires. And so this is kind of an advance on what's been done before, because most previous research on climate change impact on wildfire uses low resolution metrics of wildfire if they're making the connection directly to a wildfire characteristic. So you'll hear something like climate change is increasing the annual area burned in California by X%, say. So that's the annual time scale, so averaged over an entire year, or sometimes it will be a season, and then averaged over a large region. And what we're kind of our advance is to make these statements at this much higher resolution level. So daily time scale, we're looking at daily growth in wildfires, and then not averaged over a large region, but at the level of individual fires that have occurred historically. The other major, I would say, advance of this study is that we're not looking at fire changes in fire weather, which is what a lot of previous studies have done. So that's like one step back in the chain of causality. Instead of looking at climate change's impact directly on a wildfire characteristic, a lot of times studies will stop at the step before the wildfire characteristic itself and talk about changes in fire weather, so some type of a fire weather index. And we actually just saw that with the World Weather Attribution group that does extreme weather event analysis. They just came out with their report on the Quebec wildfires. And if you read that report, you'll notice that it's not on area burned or any type of wildfire activity directly. It's on the weather conditions that were conducive to wildfires in Canada. And so we think that this is essentially a more precise way of quantifying the impact of climate change on wildfire behavior, and it's giving us details that these previous studies had not given us.
Gotcha. So it's like there's almost two main problems in the previous research. One is resolution. The other one seems to be kind of fire weather indices. So it's like resolution. That'd be like if you had a box over San Francisco, California, United States. Pretty much the climate models had too big of a box to be able to look at individual fires. So this paper uses machine learning to be able to pinpoint actual conditions around individual fires on a day by day scale instead of like a broad kind of generalizations of like large areas and like annual burned. And then there's
Yeah.
also the problem with the fire indices where it's like, do you remember which index it is that's just temperature times wind? I forget which one that was. Might be
Hot dry windy is close to that,
it's
but
close to
it's
that.
yeah,
Yeah,
because
so
hot
it's
dry
like,
windy I think is just vapor pressure deficit times wind.
gotcha.
Yeah.
Yeah, so it's like that's kind of humans creating a formula for what we think is fire danger versus machine learning. It kind of figures out the patterns using the data itself, right?
Yeah, that would be another big selling point, is that it's if you're doing your analysis on a predetermined fire weather index that has temperature built into it, then you're going to get you know, if you have a global climate model that you increase greenhouse gas concentrations in and it gets warmer, then those fire weather indices are going to increase because temperature is in there. So you at the outset have already kind of defined what the answer to your question is going to be. And so we don't want to be begging the question in the formal logical sense. We want to have the data speak for itself. So that was one of the selling points of using machine learning and using just the natural spatial variation in temperature and interannual variation and seasonal variation in temperature to derive what the relationship is between temperature and wildfire activity. And so it's a very like hands-off approach. It's we didn't tell the models that that's the relationship between temperature and wildfire behavior. They learned that directly from the data. So that, along with the fact that the machine learning models can derive these very or can deal with these very complex interactions between temperature and all these other variables at the same time. Those are two reasons to use the machine learning.
Gotcha. So it's like if you define fire danger as temperature times vapor pressure deficit, and then you turn up temperature, it wouldn't really be surprising that fire danger increases. Whereas
Exactly.
machine learning is able to create the formula itself. So
Yeah.
that kind of also reminds me of where things are like a little imprecise. And that's often, you kind of touched on this earlier, but where we have like a huge wildfire happens, and then everybody says, like, oh, this is because of climate change, this is because of warmer temperatures. But is part of the conclusion of this paper that that's kind of an imprecise way to look at it and things are actually much more nuanced?
Yeah, in this version of the research, this is kind of, I think I consider this step one. We did isolate the impact of temperature on, in this case, the risk of extreme growth, extreme daily growth. And so in that sense, we're not looking at the relative influence of temperature change versus other important contributions like changes in ignition patterns and changes in fuel characteristics in particular. But in our current phase of the research, we are bringing those in, and in particular looking at changes in fuel characteristics, fuel loadings, and both at the surface and in the forest canopy. And when you do that, you realize that fuel characteristics have just a huge influence on wildfire behavior. And it can be, so large that if you were to scale up these hazardous fuel reductions that we're talking about that are endorsed by the US wildfire crisis strategy, that you could completely offset the impact of climate change because they do have very large leverage. So I think that type of result, what we're seeing now, and is not necessarily in this first paper, that gets to your point that it's, that these are multi-causal events, and just talking about climate change is not the complete picture.
Gotcha. Yeah, there's so many different factors that it's always tempting for humans to like just pinpoint one and then make a generalization, but in reality things are always very nuanced out there. But that's good to hear there's some hope if the fuel reduction projects actually go underway, more prescribed burning, that we could negate some of the problems with warming temperatures. But
Mm-hmm.
you started to touch on kind of like how this experiment was set up. So I know you define extreme wildfire as burning greater than 10,000 acres over a 24-hour period on individual fire. And then basically using different variables to predict when that is going to happen. Could you just kind of describe like what the process is of setting up the machine learning model and then some of the methodology to your experiment?
Yeah, so we borrowed this methodology from uh, it's often called the storyline approach, or the pseudo global warming approach in the extreme event attribution literature. And so conceptually, what that is you take a weather event or a sequence of weather events and you place it in different background climate states. So the most famous examples of this are studies that have done this with hurricanes. So it's like you take Hurricane Katrina in a weather model and you place it in 2050 or 2100 temperature conditions. So you kind of adjusting sea surface temperatures, and you see what that does to the hurricane. And so what they found is that it tends to increase rain rates at or above Clausius-Clapeyron relationship. And that's been done also with like superstorms. Sandy, put it in different background climatological states, and you find that it strengthens to some degree. And so we're trying to do the same thing. We're taking the unfolding weather around a fire and placing that in different temperature conditions. And I'll get into, we also then propagate that temperature change into fuel moisture calculations. But so overall, the idea is we know that wildfire behavior is the result of a bunch of complex factors. And so we use the well-known wildfire behavior triangle as our starting point for these conditions are going to be highly influential on wildfire behavior. And so that behavior triangle has edges of topography and weather and fuels. And so we give the machine learning models all this information on weather and fuels and topography for each fire and see how well they can predict extreme growth, or the probability of more than 10,000 acres of wildfire growth in a single day. And we do a bunch of scoring metrics on that and find that they do a good job. So if you give it this information on fuels and weather and topography, then they'll do a good job of predicting the probability of extreme growth. And we do it, it's like we train it on data and then we test it on data that it wasn't trained on, and make sure that it's not overfitting and things like that. And so then once we have those relationships established through the machine learning, then we can turn the knob of temperature to see how that changes the results. So we basically make a copy of all of those weather conditions and topographic conditions and fuels conditions, and then alter the temperature variable in accordance with what climate models say kind of background warming should be under different emission scenarios and different timeframes. And so then we can calculate that difference in the risk of extreme growth when that's filtered through the model. So we have new temperature, and then we also end up calculating new vapor pressure deficit, because temperature went up, that increases the vapor pressure deficit, and then new dead fuel moisture variables, because temperature goes up, and that decreases the dead fuel moisture content. And so then all those predictors are changed slightly in the warmer climate. And so then the risk of extreme growth changes. And that's the main thing that we're comparing then, is the risk of extreme growth in the current climate versus a pre-industrial temperature versus future temperatures in 2050 and 2100.
Nice. I feel like that was a perfect explanation. Just to make sure I have it right. So it's basically you have all these different variables around the triangle, like temperature, wind, humidity, and you have topography like slope, moisture is like fuel moisture. Do you use how many fuels are out there, or is it just the moisture aspects of fuels?
In this paper, we had a very rudimentary, actually, representation of fuels and vegetation. And since then, it's gotten much more sophisticated. So now we have fuel loads like at 1 hour, 10 hour, 100 hour live fuel loads, and then a bunch of canopy characteristics, canopy cover percentage, bulk density, canopy base height. In this previous version, we just had basically land, we had vegetation categories that were just in 3 categories. So grass, shrub, and forest. And then we also had like vegetation fraction. And then dead fuel moisture was calculated everywhere, regardless of what the surface vegetation characteristics were. So that version is pretty unsophisticated, but the models did do a pretty good job of predicting extreme growth, even without that much information about the fuels. But when we give it information about the fuels, they do much better. So this current version is promising, because we weren't necessarily trying to do this solely to increase the predictive power. We wanted to do it so that we could manipulate the fuels and do the same idea that I just said with temperature, but say, okay, let's reduce the fuel load in accordance with what we think would happen with a prescribed burn. What does that do to the wildfire behavior? And so we're seeing big deltas in that change in when you change the fuel load, what it does to the calculated wildfire behavior.
Oh man, I can't wait for the second version of this paper to come out. That sounds pretty awesome to actually be able to quantify like how useful a prescribed burn is going to be. And you could also probably figure out which areas in California you get the most bang for your buck if you did a prescribed burn, which could be very useful knowledge to have.
Yeah, that's exactly the idea. Yeah.
Nice. So you have all your variables around the triangle: temperature, wind, like fuel, topography. And then you're basically predicting whether it's going to be an extreme wildfire day or not an extreme wildfire day. You train the model on 18,000 individual fire days. I believe 380 of which were extreme fire days, so burning more than 10,000 acres. So the model is able to learn when an extreme fire is going to happen, almost just the same as like a human does, where if it's cold out, there's a lot of moisture, it just rained, and there's no fires, you think, oh yeah, today's probably not going to be a day where we see fire. But then if it's 90 degrees, super windy out, dry out, California's in a drought, your brain just kind of knows, oh, this could be a high fire danger day, because you've seen big fires pop up on days like that in the past. So like the models are able to learn the same way humans can, but to a much more sophisticated extent, because it can take into account exact data points and thousands of data points to basically be able to predict whether it's going to happen or not happen based on those variables. And then it sounds like what you're doing in your experiment is then turning the dial. I like that little analogy on temperature, and then also allowing that temperature to propagate into fuel moisture. And it sounds like vapor pressure deficit. So you're turning all those dials, and then you see what the risk was before, and then you see what the risk is now, or with the turn dials. And then based on the comparison between those two, you can figure out how important the increase in, or how much the warmer temperatures increased your fire risk, right?
That's exactly right. Yeah.
Nice. So you get your model set up, and then you get some of your results. I'm looking at those figures right there. And the first thing that kind of popped out to me was how different some of the different fires are. But then it's also broken into 2 categories. You have probability ratio, and then you have fraction of risk attributable to warming. Could you So intuitively, the second one makes like perfect sense to me, but I have to admit the probability ratio, I kind of understand what that would be, but it's not as intuitive to me. Could you just explain what the probability ratio is?
Yeah, it's just the ratio of the new risk of extreme growth versus the old risk. So if it goes from the model might say, oh, there's a 10% risk of extreme growth today in the pre-industrial climate, and in the current climate for these same conditions, except for the temperature change, there's a 20% risk. That's a probability ratio of 2, that you doubled the risk. And then the fraction of attributable risk, I actually would not use this again. I think it's confusing because you could get a fraction of attributable risk of basically 100% to climate change, but then and studies do this. We were basically following a convention by using the fraction of attributable risk, because it's something that's kind of well established and conventional in extreme event attribution. But I've discovered that I do not like it because it can be essentially you over determine the causal impacts of things. So you could this happened with the Seattle heat dome in 2021, that they did this calculation or there were papers that did this calculation with fraction of attributable risk, where they basically say 100% of the risk of that event is attributable to climate change. But then that's just a confusing way of conceptualizing it, because then it's like, well, what fraction of the risk was attributable to the sun, or there's like all these different things. It's like doesn't really make sense to say 100% was attributable to climate change. And we can get into the math of how that is calculated and what that actually means, but I would prefer just to leave it at the probability ratio. I think that's actually like a more intuitive calculation, just saying, okay, if the risk went from 10% to 20%, that's a probability ratio of 2. And so yeah, that's what that first figure is showing, is the different probability ratios for the different fire events. Or yeah, those are integrated over the lifetime of those individual fires. And you mentioned that they are very different from each other, and I think that's one of the most scientifically interesting things that came out of this study, is that we're essentially putting background warming on top of these fires that's pretty uniform. It has a function of space in California, and it's a function of month of the year, but it's not like you're having very different climate change background warming influences on these different fires. So the reason that they have different numbers in terms of their probability ratio is something else. It's not that the warming is different amongst these fires. And it turns out what that is that the models basically discovered this, or told us this, that if fires are near these critical aridity thresholds, like around 10% of dead fuel moisture or 1.5 kilopascals of vapor pressure deficit, then the warming has this outsized influence on the risk of extreme growth. So if a fire's conditions are far on the moist side of that, then warming doesn't have that big of an impact, because you're not kind of warming isn't pushing you over that threshold. And the same is the case if you're on the far dry side of that. If you're in conditions that are already very conducive to wildfires, then warming doesn't have that large of an impact on those either. It's the fire events that basically in the pre-industrial condition run the safe side, and then in the current condition and in the future condition are on the unsafe side. Those are the the fire events with these large probability ratios. And that's, I think, really scientifically interesting, and it can inform, okay, there are certain locations and times of the year that we should be paying particular attention to in terms of changing risk.
Gotcha. So I feel like that makes a lot of sense. Like if it's really moist out in the environment and then you turn the dial on temperature, and then it's still really moist out, your model's still probably going to predict no extreme fires. And then if it's super dry out, you turn the temperature dial, it's still super dry out. So it's probably going to be predicting extreme wildfires no matter what. But then it's in that little, like, you call it thresholds, or like that little Goldilocks zone where maybe you wouldn't have had a fire, but then you turn the dial and then it like crosses that threshold. So then that's where your probability ratio massively increases. That does remind me of one of the biggest questions I had when reading this, because you say that, so it has to do more with like that threshold, how close it is to the thresholds, than different climate data. So that made me think about what is the climate data that you're using? Like, is it uniform across all of California? Like low emissions, everyone increases by a degree, high emissions, everyone increases by like 10 degrees, or is it broken down to actual like places like NorCal increases by half a degree, but Southern California 2 degrees? So what's the resolution on that? And then is it also just for like daytime high temperatures? Or is it like, I remember Mike Voss saying that like afternoon highs actually aren't increasing as much as like the overnight lows. So does it like take into account that? And then finally, what is like, who's making the low emission scenario versus the high emission scenario?
Yeah, so these are, at least in the current version and in the supplement of this paper, we're using the Cordex dynamically downscaled climate model output for the change in temperature. And so that is at a 12-kilometer resolution. So, and it's uniform, it's like averaged over 30 years. So what you're trying to, so the models will produce temperature output, at arbitrarily kind of high resolution. They have time steps of say 30 minutes or something like that. But you average over the models to get what the climate change component is, or you average over time, and we do end up averaging over multiple models to get what the central estimate of the change in temperature is. But it will retain that spatial resolution of 12 kilometers. And it also retains any type of seasonal variation in that warming. So it's a separate calculation for each month of the year. So that delta, which is a function of space, so 12 kilometers, and time of the year or month of the year, is what's appended to each wildfire events to see what the impact of climate change is. And it's a daily mean temperature. So it's not a daily high or a daily low. It's a daily mean. And that agrees with the predictor variable that we're using also, because the predictor variable is also a daily mean. Where I know in your paper, I think you used daily high temperatures.
Gotcha.
But yeah, and then the emission scenarios are these standard emission scenarios that come out of they're now the SSPs and the RCPs, but they're the standard scenarios that have been used in climate modeling for a long time. And so there's this RCP 8.5, RCP 4.5, and RCP 2.6. And that's a whole other discussion of how plausible and likely these scenarios are. So for a long time, for example, RCP 8.5 was called business as usual. And especially in the past decade, and others would argue going back to its inception, it has been deemed to be very implausible, that it's way too high, way too much emissions, in terms of if you just look at the energy landscape of the world, that RCP 8.5 is essentially like if we went way out of our way to go and dig up all the coal that we possibly could and burn it. And that's just not what the, geopolitical landscape is calling for now. So we do show RCP 8.5 in our study, but I think it should be phased out in future studies and not be something that's shown, and certainly not highlighted as some type of a business as usual situation. And so I think probably the more interesting comparison would be RCP 4.5 versus RCP 2.6, which is something that's kind of more in line with the Paris Agreement. So that would be comparing something that's more like a no climate policy global situation to a climate policy situation. And something interesting that comes out of that is, if you look at our difference between RCP 4.5 and RCP 2.6 by 2050, that difference is almost nothing. So that's telling you, there's a huge difference in terms of what that would mean geopolitically in terms of climate policy, but you're not seeing that come about in wildfire risk by 2050. Those things only really make a difference in the latter half of the century into the next century, really. So that tells you that, if you want to solve the wildfire problem on any time scale that people, alive today care about, then you're not going to be focused exclusively on emissions reductions. You would have to go to something more direct, on the ground solutions, like scaling up these hazardous fuels reduction treatments, something like that, something more direct on the ground.
So just one quick clarification: is the very high emissions scenario in this paper, is that like the 8.5 one that you said?
Yes.
Probably isn't going to happen.
Yeah.
Gotcha. So that one is like, there's the natural progression of energy. We've gone from like coal, which emits a ton of CO2, to like natural gas, which is like a lot better than coal. And then maybe if we're to switch to wind, solar, and nuclear, it'd just be continual improvements in reductions of CO2 per energy unit created. So the very high emission scenario would be like if we were just burning coal like crazy, which probably isn't going to happen. So then it's more the low emission and sounds like the medium emission scenarios that are the most probable. Low emission would be if we maybe like switch to clean energy super quickly, and then there's almost like no emissions.
Yeah, RCP 2.6 is that low emissions, very low emissions one that you're mentioning there. And that's a scenario that's net zero emissions by about 2070. So you hear a lot about net zero by 2050. That would be something that would potentially limit warming to 1.5, limit global warming to 1.5 degrees Celsius above pre-industrial levels. I don't think any clear-eyed energy analyst thinks that that's achievable. It's essentially like the same thing as taking the reduction that we saw during COVID and having the reduction in emissions that we saw during COVID and having that play out every single year until 2050. So it's that level of reduction compounded continuously until 2050. I don't think that's going to happen. Net zero by 2070 also, I think, is probably implausible. I think we're right around, we are potentially plateauing emissions right around now, but I think it's going to be a long plateau and long decline, maybe net zero by 2100 type of situation. So that's in between then this RCP 4.5 and RCP 2.6 scenario.
Gotcha. So it sounds like the middle scenario is probably the most likely to happen, and there might actually be some good news there. You could call it a silver lining. That sounds like by the middle of the century, that's in terms of extreme wildfire risk, that's actually not that different from if we took like drastic action to reduce emissions now. But then there's more of a risk as you go farther out into the future.
Yeah, I'm just making the point because I'm not comparing today to the future. I'm comparing the different emission scenarios to each other in 2050
Mm-hmm.
and saying that, yeah, the different emission scenarios between very high emissions and low emissions and very low emissions in 2050, that difference in terms of wildfire risk is very, very little. So like, I guess the perception that I'm trying to clear up there is the idea that, like, oh, we have this wildfire problem. Our solution is to go and pass climate legislation that reduces emissions. Like, that will make an effect if it's global, and if we're talking about in the 2100s, but it will not make effects. It will not make an effect if it's not global, if it's local only. And if we're talking about these timeframes of, say, 2050, the next couple of decades, it's just the inertia in the Earth system. You don't stop warming until emissions are at net zero. And so you just don't see that divergence of the influence of the different emission scenarios on wildfires on timescales that people plan on.
Gotcha. So any solutions that we're looking at, we'd probably get the most bang for a buck if it was like fuel reduction through prescribed burning, as opposed to drastically reducing emissions, just because there's not that big of a change by 2050, as long as you're not going business as usual, probably. But there was one thing that I noticed in the like, this is now figure 2 C and D, is it looks like in the low emissions scenario between middle century and end of century, and then you can actually see this well in G as well. It seems like those are almost the exact same. So is that basically just because it's saying by the middle of the century we would have almost already leveled out, and then there'd almost be no more warming, so end of the century is almost the same as middle of the century?
Yeah, that's exactly right. In that very low emission scenario, you are essentially halting warming by the middle of the century. And so you're just staying steady by the end of the century.
Gotcha. And then also in G, the one that kind of sticks out is that very high emissions end of the century. And just to try to quantify what that's saying, even if that one is implausible, would that be saying that by the end of the century, in a very high emissions atmosphere, the fires that we saw from 2003 to 2020, if we had 380 extreme fire days, we would have had double that number?
Yeah. Yep. We would have, 786 is what that calculation is saying.
Gotcha. And then so looking at G still, which of those arcs do you think is the most likely to happen in the future? Or would it be like the middle scenario, which isn't illustrated there?
Yes, I would think I do think it's the middle scenario that's not illustrated there.
Gotcha.
And that's me speaking so I'm also, co-director of climate and energy at the Breakthrough Institute. And so I'm very adjacent to a lot of energy conversations. And so that's not something that obviously that comes out of this study, because these are inputs to our model. Just want to clarify that there's nothing in this study that's on the actual energy system or on the emissions. But speaking just as someone who is kind of attuned to these conversations and this research, I would say that middle, that RCP 4 point, somewhere between RCP 4.5 and RCP 2.6 is probably the most likely from an emissions perspective. And so that would be, yeah, it would be between that dashed red curve and the dashed yellow curve.
Gotcha. So then, do you remember what the numbers for that one are? Like in terms of the probability ratio or percent risk?
Yeah, I have that here actually. If you put those on G, the 2050 number for RCP 4.5 is 474, and the end of century for RCP 4.5 is 550. So that 550 would be overlapping with that dashed red curve, and 474 is right in between those two.
Gotcha. So it would have been a little more than 500 extreme wildfire days instead of the 380 that we actually had in that middle emission scenario.
Yeah.
Gotcha. I think that all makes sense. And then just going on to figure 3. So for A and B, that's like talking about how many dials you're turning, right? And then so whether it's temperature, vapor pressure deficit, or like 100-hour fuels or 1,000-hour fuels, which variable when you turn the dial was the most important or played the biggest role?
Yeah, so what this figure shows is a bunch of all of the different combinations of variables where temperature change is propagated into them. And it's looking at what the probability ratios were for all the individual fire days when you do that one at a time. And we show that 100-hour dead fuel moisture is the most important, followed by vapor pressure deficit, followed by 1,000-hour dead fuel moisture, followed by temperature. So temperature itself is the least important of those 4, which is in line with previous research on fire danger and on climate change's impact on fire danger, that it's not that you're literally warming fuels closer to their ignition point that is what temperature is doing. It's the warming temperatures are drying out, or they're increasing the vapor pressure deficit of the atmosphere, and so allowing more moisture to move from the surface to the atmosphere, and that's what's increasing the fire danger. And so we see that in a bunch of different combinations, but that the far right part of that panel is looking at each one individually, and so they're ranked, and it's 100-hour vapor pressure deficit, 1,000-hour temperature.
Gotcha. So it's maybe less incorrect to say this fire was as bad as it was because of the temperature, but it'd be maybe more correct to say this fire was as bad as it was because the warmer temperatures dried out the fuels.
Yep.
Gotcha.
Yep.
And then, so for C and D in this panel, I think the main point that you're maybe making there is talking about the threshold, but then also the diminishing returns. And I had to think about the diminishing returns thing probably a bit longer than I should have for it to make sense. But is that basically saying, like, if you have 30-degree or 30% fuel moisture and you crank up the temperature, it might drop down to like 25. But if you have 5% fuel moisture and then crank up the temperature, it might just drop down to like 4.5.
Yeah. I mean, I think in absolute terms, increasing temperature has less of an impact on dead fuel moisture when the fuel moisture is very low as opposed to when it's high. So the same, 1 degree Celsius warming, if you're already at 1% dead fuel moisture, you're not going to get to -3% or something like that, right? You're right at your limit already, and so it's not gonna make that big of a difference in terms of the percent of fuel moisture change. Where exactly like what you just said, if it's at starting at 40%, then 1C increase could get you 5% reduction, say, in dead fuel moisture.
Gotcha. Yeah, it almost reminds me of like learning a sport or like learning chess or anything like that. Whereas like if you were to start tennis and then do a couple lessons, you might double your skill. But then Novak Djokovic, like the best tennis player in the world, he'd be happy to get like a fraction of a percent better each day.
Yeah, definitely. Right. Notice that I remember, studying for tests, right? That like at the beginning, well, at the beginning, maybe you're kind of at the bottom of the S curve, and then you start getting more and more. And so then you're at this like high learning rate, but then you start saturating eventually, like you're just, looking at random things that are very unlikely to be on the test. And so you've done
Yeah.
most of what you can do.
Yeah, diminishing returns. At that point, you can maybe put the books away and take a little brain break at that point.
Right.
All right, so figure 4, I feel like this one packs in almost all the information you need to know about this paper. There's a lot going on and some pretty interesting things can come out of figure 4. So A and B, that's looking at car fire versus North Complex fire. And then on the y-axis, we're looking at daily growth. So how many acres burned each day. And then where you have the magenta circles, that's where you have your extreme fires greater than 10,000 acres. And then below that, we got probability. And then below that, probability ratio. And the first thing that kind of stands out to me is that the probability that you have an extreme wildfire is higher for the car fire than the North Complex fire, but the probability ratio for the car fire is almost nothing, whereas the North Complex has a huge probability ratio. So can you explain like where those differences come from?
Yeah, then the next 2 panels are trying to explain that then I have that I mentioned before, that the 2 most important explanatory variables in terms of what the models tell us are 100-hour dead fuel moisture and vapor pressure deficit. And so for the car fire, that was a fire that occurred. So the different lines are the different climates. And so what that's showing is that even in the pre-industrial condition, it was very dry and very, high fire danger. And so it was, the dead fuel moistures there are at or below 6%. And then the vapor pressure deficits are very high in all of the different climates, so above that 1.5 kilopascals. And so what that means is that the models are predicting high probabilities in all of those cases. And there's just not that much difference. There's not that much impact of warming on those probabilities relative to each other, because they're all high in terms of that ratio, right? And so then you see that in panel E as low ratios, where the North Complex fire was kind of straddling these critical thresholds. So in the pre-industrial condition, you're spending more time on the safe side of that 100-hour dead fuel moisture threshold. So you're above 10% for some of that time, or you're kind of right around 10%. And for vapor pressure deficit in a pre-industrial condition, you're also spending time below that vapor pressure deficit threshold, so below that 1.5 kilopascal difference, where then you turn that temperature knob, you turn that warming, and you start breaching that threshold more in both of those cases, where then in the extreme very high emission scenario, the RCP 8.5 scenario, the whole length of the fire is below 10% of 100-hour dead fuel moisture, and almost the entire lifetime of the fire is above 1.5 kilopascals of vapor pressure deficit from that change in the background state. And so in that case, then you're getting these very large probability ratios. So this is telling the same story that we talked about with figure 2, looking at the differences in space, but this is just the differences in time. And that story is that climate change has a different impact on different fires depending on if climate change pushed conditions over these critical aridity thresholds or not.
Gotcha. So, like looking at the car fire, that was a 6% fraction attribution to warming, versus North Complex was a 26%. And the main reason for that was because car fire, you're pretty much going to have an extreme wildfire day, no matter what atmosphere you're talking about, no matter which emission scenario you're talking about. Whereas North Complex was right on that little boundary where it was that increasing the dial really pushed it over the edge into that extreme territory.
Mm-hmm.
Nice. And then, so kind of key point there sounds like it's that different fires can be very different from each other. And the main reason for that is because different fires are on closer or farther away from that threshold. But then I also thought it was interesting looking specifically at figure 4F for the North Complex, where it even changes a ton within a fire itself. So I feel like that just really drove home the point of how nuanced this is. It's like you not only can't say, oh, this fire was bad because of warmer temperatures, you'd have to say what percent of the risk increased because of that, and then you'd also have to break that down by the day that you're talking about.
Yeah, and there's something else is that shows is kind of how small the background climate change temperature changes relative to day-to-day weather variability, because that's the only way that you could get these large differences day to day depending on the weather of that day, is that the climate change signal is relatively small compared to natural variability on high spatial end time scales, and so that's an interesting result in and of itself is being able to see it like that.
Oh, so that's interesting. Just want to make sure I understand that right. So it's basically saying, like, as long as your fire is happening within the same month and the same 12 kilometers, you're going to be using the same level of increase.
Yeah.
So it's interesting that the probability ratio changes so much. So that also is further evidence for the fact that, like, on some of those days you're right by the threshold, and on some of those days you aren't going to be, because the dial change is the same, but that same dial change can have like drastically different impacts depending on the other conditions.
Exactly right. Yeah.
Nice. That is very interesting. And then towards the end of the paper, you also talk about how, like, this is kind of an idealized scenario where you're talking about temperature and what temperature propagates into, like fuel moisture and vapor pressure deficit. But there's lots of other things not accounted for, like most likely an increase in fire ignitions as population increases, increase in fire season length, which is, we've seen that in a lot of research. But then it also doesn't account for things that might reduce extreme fire days, like how many prescribed burns that we do. So Do you think the numbers, and I guess this would almost be probably more of like a personal opinion than scientific, but do you think the numbers in this would be kind of overestimates of what are going to happen, underestimates of what might happen by 2050, 2100? Or do you think that really just depends on what we decide to do today, and maybe in particularly in terms of reducing fuels as opposed to reducing emissions?
Yeah, I think you can make a case for either one that sounds relatively convincing.
Hmm.
So I don't think it's obvious what direction. So I think what you just said is very true, that this doesn't account for an overall change in season length, which would impact obviously the total number of extreme growth days that you get. And it doesn't account for other things that we hold constant, that I think it actually is justifiable to hold constant, because there's no reason to believe that, or there's no strong evidence that they would change things like precipitation, things like wind. But yeah, the fire season length is probably a big one. I'm not sure about ignitions changes. Hopefully you could reduce ignition changes with public information campaigns, and maybe changes in vehicles, that you get less vehicle ignitions, or changes in utility practices. So I'm not sure about ignitions. I would say that the elephant in the room is the fuels component. So both looking historically, we're not quantifying changes. We're not quantifying the impact of the buildup of fuels to unnatural levels due to policies where we, suppressed all wildfires in the 20th century. So we're not accounting for that historically, and we're also not accounting for management practice changes going forward in the future. And as I mentioned, our preliminary results are showing that those changes in fuels could have very large impacts on wildfire danger. And so I would hope that if we could get those projects scaled up, and there's a lot of hurdles to that, legally and politically, but if we could achieve the stated goals of, California has a stated goal of treating 1 million acres a year. U.S. Forest Service has a goal of 50 million acres, I believe, by 2030. These are numbers that would have a large impact, according to our models, in terms of, they could not just, we're going to offset the impact from climate change a little, but again, totally offset it, or totally negate it, such that you could have a future of less wildfire danger despite climate change.
I feel like that's a huge takeaway too. And it's pretty good news. And it's also maybe something I've heard a lot in the fire community, like talking to different wildfire experts out there. It seems like all of them are hammering home the point of prescribed burning and reducing fuels. Like that's the answer. So it's pretty cool that you come from it from like a completely different direction, and basically provide the evidence that, like the scientific evidence that that is actually the case, which is pretty cool.
Yeah, and so I wish that we had done that in this initial paper, but this initial paper is just this first step of isolating the climate change impact by itself. And then I think the natural, that's, I did that because I'm a climate scientist, and that's my natural first thing to do. But if I was more, coming from the fire science background, where the mindset is much more around fuels, then maybe that would have been the first thing I did. And so regardless, it's important to have them both in there if you're actually, thinking about like literally predicting the future and not just thinking about some hypothetical situation of if we held everything constant and only looked at the climate change impact, what is that? That's an interesting thing to look at scientifically, but it's not all that practically meaningful when you know that all of these other causal factors are changing at the same time.
Nice. Yeah. So this paper already had some super interesting results. Sounds like you have another paper on the way that is going to be potentially even more impactful out there. So that's going to be great to stay updated with as well. Definitely want to talk with you again once that one comes out. But yeah, thanks for talking with me today.
Yeah, thanks a lot. Thanks for having me.